Hi, we'll talk about partial derivatives. This is Stewart section 14.3. I'll introduce partial derivatives, including the limit definition of partial derivatives and explaining what they mean geometrically. Then we'll talk about how to realistically compute partial derivatives, and not with limit definition, but using actual differentiation rules. And then we'll talk about higher order partial derivatives. So just to take a step back, let me remind you some things about the derivative in one variable. So remember that if I have a function f of x, then the derivative f prime at a point A is given by this limit as h goes to 0 of this fraction, which is called a difference quotient. So the difference f of a plus h minus f of a divided by h. And what this is referring to is a slope of a line where on the graph, this sort of parabola-looking graph of y equals f of x, we're taking 2 points. We're taking the point where x equals a and marking that point on the graph. And then we're taking the other point where x equals a plus h, and we're marking that point on the graph up here. Now the horizontal distance is 8, and we're connecting those 2 points with a line, which is this orange line. The difference quotient is the slope of that orange line, right? The first point is at height f of a, and the second point is at height f of a plus h. And so the difference between them, the y difference, is f of a plus h minus f of a. And the horizontal distance is the distance between a and a plus h, so the distance is h. So this fraction is just rise over run for the slope of that orange line. And then when we take the limit as h goes to 0, that means that we're sliding these points together. And so our points on the graph are going to come together. And this orange line that's drawn through those 2 points is going to become a tangent line. This line becomes a tangent line. Or if you want to be technical, it's becoming closer and closer to I don't know if we ever reach the end of that limit, but the point is that these orange lines approach the tangent line, so the slope approaches the tangent line slope. And that's what the derivative is. It's giving the tangent line slope. Okay, so that's what happened for a function of one variable. Now for a function of two variables where z equals f of xy, we have what are called partial derivatives. We can do the same kind of difference quotients, but with respect to x or y. And those are going to be two separate things. So we can, the first thing that's written here in the first equation, I have a difference quotient f of a plus h comma b minus f of ab divided by h. So the first variable, the x variable, we're putting a difference, a plus h versus a. But the second variable, y, is staying constant. It's just staying at b. In the second line, there's a difference quotient that goes the other way. In this second one, the first variable x is staying constant. It's just x equals a. It's not changing. But the y variable is being given a difference of b plus h versus b. And in both cases, we're still dividing by h and taking the limit as h goes to 0. So we're still taking 2 points on the graph of f and finding the slope of a line that connects them. But now what's happening is that these two lines are a little bit, well, they're going in different directions, as we'll see on an upcoming slide. So these things are limits of difference quotients. So they're, in that sense, they're just like the single variable derivative that we just reviewed, and they're called partial derivatives. So this function z equals f of xy has two different partial derivatives. It has an x partial derivative, which is the first one, and a y partial derivative, which is the second one. There's notation for these. One style of notation is to write a fraction like this, and this symbol is called the partial symbol. So I would just say partial f over partial x. Or partial derivative of f with respect to x. And in the second line, there's similar style of notation. So this could be called partial derivative of f with respect to y. So it's telling you which function are you taking the derivative of. Like if you have an f, a g, and an h, and three other functions in your problem, which function are you talking about? We're talking about f, partial derivative of f. And then which variable are you differentiating? Is it with respect to x or with respect to y? So we use this partial symbol. This is very similar to single variable calculus df dx. But we use the partial symbol because these are partial derivatives. There are other kind of derivatives that can be discussed later on. So this is a kind of a specific thing, and it has its own symbol. The other style of notation for partial derivatives is what's written here, fx or fy. It's definitely shorter than writing a whole fraction, so sometimes that's just convenient and easier to write. So f is a function, and fx means the partial derivative with respect to x of that function, and fy means the partial derivative with respect to y. So let's work out a partial derivative actually using the limit definition. If you've done this in single variable calculus, then you might remember that it takes a little bit of work. It can be done, but then after you get the hang of this, you start learning about the power rule and other quick ways to do derivatives, and those are much quicker. So in practice, you wouldn't use this limit definition on a day-to-day basis. But I'm going to do an example here. So perhaps you might be worried, like, oh no, I'm going to have to use the limit definition. No, don't worry about that. On the upcoming slides, I'll show some graphics and explain the geometric graphical meaning of partial derivatives, and then we'll actually see how to use ordinary derivative rules like the power rule and the product rule and so on. So that's coming up. But just to start with, let's do one example just to see how the limit definition works. So our function is f of xy equals x squared y cubed, and I would like to find the partial derivative with respect to x. At a point AB, Well, according to the definition, I take the limit as h goes to 0, and I take my function f, and I'm going to plug in 2 points. Since I'm taking the partial derivative with respect to x, that means that x is the variable that's changing. So I put 2 different values for x. I'm going to put x equals a plus h and x equals a. On the other hand, the other variable that isn't x is staying the same. So y just stays the same at y equals b. And we're dividing by h. All right, so we have to work out that limit. Well, we are given a formula for f. F is x squared times y cubed. And then again, f of ab, x squared would be a squared, and y cubed would be b cubed, divided by h. All right, what can we do to simplify this? Oh, I guess we could pull out a common factor of b cubed. I guess we could multiply out these squares. It looks like the a squared terms cancel. And it looks like this h in the denominator, I can divide it into the numerator. Okay, that simplified a lot. This, where we are now at the end of what we've written so far, is much simpler than what we started with. And now we can take the limit. When h approaches 0, this just approaches 2a times b cubed. So that's the partial derivative, or a lot of times this will just be written as partial f of partial x. So not plugging in a particular point, but just leaving it with x and y. I worked out this example with plugging in a point AB. Even if it was an unknown point, I still plugged it in, but you could just leave it with xy if that's what you wanted to do for whatever you're working on. Okay, so we'll add some context to this later on, and you'll see how that ties in with the power rule. It's no coincidence that the derivative of x squared is 2x. So we'll see more about that later on. I won't go through it in these slides, but if you find the partial derivative of f with respect to y instead of x, you should get 3a squared b squared. And in this exercise, if you really want to do it, you should use the limit definition. We'll soon see some very short and quick ways to find this, but if you want to give yourself a small challenge, try using the limit definition. All right, let's talk about the geometric meaning of the partial derivatives. So I started this segment of this video by talking about how the limit definition of derivatives for single variable functions corresponds to slopes of lines. And we can do the same thing for partial derivatives. So let's take the graph of a function. So this blue surface is a graph of the function. It's the graph given by z equals f of xy. And on this first chart, you can see a point AB is marked, and you can see that in the graphic they've marked two curves passing through the point above AB on the graph. And those are the vertical traces of this graph. So we're going to start with the vertical trace given by the plane y equals b. So on the y-axis, we're marking the value b and just setting y equal to b, but x can be anything and z can be anything. So we get this vertical plane. This is the plane y equals b. Oh yeah, it's printed here, the plane y equals b. And that cuts through the graph along one of the two trace curves that was shown in the first image. And along that trace curve, there's a tangent line. So what's written on the slides is that let's say that C is that trace curve. So C is this trace curve. Then the tangent line to C at this point is has a slope given by, well, if this was a regular function, if there wasn't a y thing, if there was just x, if it was just a regular single variable function, the slope would be given by the derivative of that function. Well, we know what function it is. It's the function where we take the formula of f and we set y equal to b, and then there's just one variable left over in our formula, just the x variable. That's a single variable function. That's the function that this graph is showing, and the derivative would be given by the slope would be given by the derivative of that function. So the slope is given by the derivative of this function f of xb, where x is a variable and b is a constant. But taking a derivative of this function f of xb is the same thing as doing the partial derivative fx, or with fraction notation, partial f over partial x. It's the same thing. So that's what the partial that's what the partial derivative means. It means the slope of the tangent line at that point to the trace curve given by setting y equal to a constant. On the next slide, we'll see what happens with x. So on this slide, we're focused on the vertical trace that we get from the plane x equals a. Instead of setting y to be a constant, we're setting x to be a constant. So along the x-axis, we're looking at value a, and we just set x to be a. Y can be anything and z can be anything, but x has to be a. So this is the plane x equals a, and it intersects through the graph of the surface along this highlighted blue curve, which is one of the trace curves that was shown in the first image. That trace curve through the point has a tangent line, and the slope of that tangent line is the partial derivative of our function f. It's the partial derivative with respect to y. So in that partial derivative with respect to y, we're setting x to be a constant a, and we're allowing y to be a variable, and the resulting derivative gives the slope of this tangent line. So just for a moment, I'll go back to an earlier slide with the limit definition of derivative, just to highlight how in the partial derivative with respect to x, y is treated as a constant, and in the partial derivative with respect to y, x is treated as a constant, all the way back in the original limit definition. So I'll go back to that slide now. All right, so in this slide, in the partial derivative with respect to x is a variable, y is a constant. And look, y equals b. And x is a variable. Y equals b is a constant and x is a variable. In the second one, which is partial derivative with respect to y is a variable and x is a constant. And looking at this, x equals a is constant. No matter what h is, x isn't changing. And y is the variable. So setting y equals b corresponds to restricting ourselves onto that vertical plane where y equals b and not being allowed to move off of it. And setting x equals a corresponds to restricting onto a different vertical plane, the x equals a vertical plane. That's why we're cutting with those vertical planes and getting those vertical traces. And here's a summary of what we've been saying, just to recap. The partial derivative of f with respect to x at a point AB is the slope of the tangent line to the vertical trace that you get on the graph of f when you set y equal to b. You set y to be a constant, so we're treating y equals b as a constant and we're leaving x as a variable. The other one is the other way around. The partial derivative of f with respect to y at a point AB is the slope of the tangent line to the vertical trace of the graph of f when you set x equal to a. So in this case, for the partial derivative of f with respect to y, we're leaving y as a variable, but we're treating x equals a as a constant. Coming up next, we'll see how to use derivative rules to find these partial derivatives.